This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is compressed liquid water. We are asked to find some properties of compressed liquid water. The property is internal energy, and we're asked to look at 30 bar and 50 C. We're going to do this two ways. One is from a table specifically for compressed liquid water. That's the most precise way. And then we're going to look at an approximation using information from a saturated liquid table that sets the temperature correctly and neglects the effective pressure. But let's do the precise way first. We need a table, a compressed liquid table. Let's take a look. Here is a table for compressed liquid water, and it has data in blocks. Here's a block of data at 25 bar, and the property we're looking for, internal energy, is a function of pressure in this block and also in temperature down this column. But we're looking for 30 bar, not 25 bar. And let's look over at this block. The next highest pressure is not 30 but 50. So the table is coarse, and we're going to have to interpolate across pressure to get the right value. In temperature, we're asked to find 50 C, and we've got data at 40 and 80 C, so it turns out we're going to have to also interpolate on temperature. So the closest values are internal energy at 25 bar, and nearby temperatures are those two values, and internal energy at 50 bar. The values that are closest in temperature, the bracket, the value we're looking for, are these two. And let me take these values and put them on the other, they're printed on the other sheet. Let's think about how we're going to use these in making sense of this. So here's the values that came from that table. Oh, by the way, what is that table? That is the name of that table was table A5 on page 899, and then you want to add, which book. So you need to say exactly which book you're talking about, plus the name of the book. All right, now that we've identified which table, we can pull that information in, and here's the values at 25 bar that we picked out, and the values at 50 bar that we picked out, and they bracket the pressure that we're looking for, and they bracket the temperature that we're looking for. All right, so it turns out we're going to have to interpolate more than once. When we're done, I'm going to fill in the value here, which is at the right temperature and pressure. But in the meantime, we've got to take it step by step. To start with, let's interpolate across temperature at 25 bar. Let's look at that distance there, which is going to be 50 minus 40 centigrade. And let's divide by this distance here, which is going to be 80 minus 40 centigrade. And I'm looking for this value in here by this interpolation. And the first distance, let me call it the analogous distance, let me call it U minus the lower value, 167.25. By the way, these are U values, and these are U values. The total distance in the U column is going to be 334.29 minus the lower value, 167.25. And if we take this and solve for U, for this first interpolation, I'm going to get 209.01, and that's in kilojoules per kilogram. So let me transfer that up here and say 209.01. So that takes care of finding the right temperature, the value at the right temperature at 25 bar. We're going to repeat this over here at 50 bar. And I won't go through the details, but when we're done with that temperature, interpolating across temperature, the internal energy here is 208.64. And then finally, we have to interpolate across pressure. And interpolating across pressure would be relating the distance between 30 and 25 bar and the distance between 50 and 25 bar. When we do that, the final answer, the final number, is going to be 208.94. So the answer is that internal energy at 50 C and 30 bar by interpolating on the compressed liquid table is 208.94 kilojoules per kilogram. Now, that's the hard way. To get that, I needed 3 interpolations. Let's look at an alternative way, an approximate way. The idea is for compressed liquids, the value that I want is close to the saturation condition, so I'm going to use the correct temperature, and I'm going to ignore the effective pressure. Now, this works for liquids only. If you take a liquid and you compress it, imagine you've got this blob of liquid and you squeeze on it with pressure, it doesn't change its value much. It doesn't change its shape. Therefore, the properties don't change much either. Okay, so we're going to look at a saturated liquid table. I have to identify the table with a book and a page number. And let's go look at a saturated liquid table. See what information we've got. Here we are. Here's a water table, saturated water, a temperature table. We're interested in internal energy for saturated liquid conditions, and we're looking for the correct temperature, and we're lucky now that we have the value we need is 50 C, so we're going to go across here until we get to the saturated liquid value for internal energy that we're looking for. Let me see if I can blow that up a little bit. The value that we're looking for at 50 C is 209.32. Let's copy that to the other page. So I'm going to say that the internal energy we're looking for compressed liquid at 50 C and 30 bar is approximately equal to U for saturated liquid. Again, this only works for liquids at 50 C, and the P saturation. Now, how far off are we? Well, if we looked at, I didn't mention this when I was looking at the other table, the saturation pressure is 0.12 bar, so it's way off. But the value is 209.32 kilojoules per kilogram. So the temperature was right, and the pressure was not. But that's pretty close. How close is it? Well, what's the error? Let's talk about that. The error, let's see, the good value is 208. Well, I guess I want to take this one's bigger. Stop that. 209.32. I'm going to subtract off the good one, 208.94. When I do that, I get 0.38. Now, using this approximation, if the change in internal energy in your problem is much bigger, what does that mean? Maybe 100 times bigger than the error. Stop that. Hundred times bigger than that would be about 40 kilojoules per kilogram. All right, let's recap. We're asked to find properties of, I'm having trouble scrolling today. We're asked to find properties of compressed liquid water at a particular pressure and temperature. The accurate way is to use the compressed liquid table. Please state which table you're using. But that might require interpolating 3 times in the worst case, when the value that you need doesn't line up with the table. As an alternative, if the delta U in the problem is large, we can use the saturated liquid value, and at most we're going to have to interpolate maybe 1 time. So this is easier. And if you remember that you can use this trick when the delta U in the problem is big, then all will be well.